Consider an electric dipole consisting of charges plus Q and minus Q, separated by a small distance 2a, with its axis placed along the x-axis and the midpoint of the axis of the dipole at the origin. The charge plus Q lies on the positive x-axis at A, and the charge minus Q lies on the negative x-axis at B. The electric dipole moment P due to the dipole is equal to 2aq, and the dipole moment P points from minus Q towards plus Q. Let this be equation 1. Consider a point P in the electric field of the dipole in free space, at a distance r1 from the charge plus Q, and distance r2 from the charge minus Q. The net electric potential at point P due to the electric dipole is equal to the algebraic sum of the electric potentials due to the charges plus Q and minus Q of the dipole. And is equal to 1 by 4 pi epsilon naught into Q by R1. Similarly, the electric potential at point P due to the charge minus Q is V2 and is equal to minus 1 by 4 pi epsilon naught into Q by R2, since the charge itself is negative. According to the principle of superposition, the net electric potential at point P due to the electric dipole is denoted by V, which is equal to V1 plus V2. Substituting the earlier expressions for V1 and V2 in the equation for V and simplifying, we get the net electric potential V is equal to Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Let this be equation 2. Theta is the angle made by line OP with the direction of the electric dipole moment. From the geometry of the figure, using the cosine rule for the triangle PAO, we have R1 square is equal to R square plus A square minus 2AR cos theta. This can be written as R1 square is equal to R square into 1 minus 2A cos theta by R plus A square by R square. Let this be equation 3. If R is much greater than A, then the ratio A to R is much less than 1, and hence the term A square by R square in equation 3 can be neglected as it becomes very negligible. Then we get R1 square is equal to R square into 1 minus 2A cos theta by R. This implies R1 is equal to R into 1 minus 2A cos theta by R power half. Therefore, 1 by R1 is equal to 1 by R into 1 minus 2A cos theta by R power minus half. Using binomial expansion of the terms in parentheses, we get 1 by R1 is equal to 1 by R into 1 plus A cos theta by R. Let this be equation 4. Similarly, using the cosine rule for triangle PBO, we have R2 square is equal to R square plus A square plus 2AR cos theta. This can be written as R2 square equal to R square into 1 plus 2a cos theta by R plus a square by R square. Let this be equation 5. If R is much greater than a, then the ratio a to R is much less than 1. And hence, the term a square by R square in equation 5 can be neglected since it becomes negligible. Then we get R2 square is equal to R square into 1 plus 2a cos theta by R. This implies R2 is equal to R into 1 plus 2a cos theta by R power half. Thus, 1 by R2 will be equal to 1 by R into 1 plus 2a cos theta by R power minus half. Using binomial expansion of the terms in parentheses, we get 1 by R2 is equal to 1 by R into 1 minus a cos theta by R. Let this be equation 6. Substituting equations 4 and 6 in equation 2 and simplifying, we have V is equal to 1 by 4 pi epsilon naught into Q by R into 2a cos theta by R, which will be equal to 1 by 4 pi epsilon naught 2a Q cos theta by R square. We know that the dipole moment P is equal to 2aq, and hence net potential V is equal to 1 by 4 pi epsilon naught P cos theta by R square. Let this be equation 7. If R cap is the unit vector along the direction of OP, and since P dot R cap is equal to P cos theta, then we have net potential V is equal to 1 by 4 pi epsilon naught into P dot R cap by R square. The potential V as obtained by equation 7 is for the distance R, which is very large compared to A. If we consider point P on the positive x-axis, then the angle between the position vector of point P and the dipole moment of the dipole is 0. Then the potential at P due to the dipole V is equal to 1 by 4 pi epsilon naught into P by R square, as cos 0 degrees is equal to 1. If point P is on the negative x-axis, then the angle between the position vector of P and the dipole moment of the dipole is 180 degrees. The potential at P due to the dipole is V is equal to minus 1 by 4 pi epsilon naught into P by R square, as the cosine of 180 degrees is minus 1. For any point on the equatorial plane of the dipole, the net potential will be 0. Since plus Q and minus Q cause equal positive and negative potential respectively on the plane, and as theta is equal to 90 degrees. Therefore, cos 90 degrees is equal to 0. When the position vector R is rotated about the dipole moment vector P, keeping the angle theta fixed, then the points corresponding to P on the cone generated will have the same electric potential. We also observe that the electric potential V due to the dipole is inversely proportional to the square of the distance of the point of observation in the electric field of the dipole. In the case of a dipole, we have calculated the net potential due to a system of two charges. Now, let us consider the electric field due to a system of charges. Say, Q1, Q2, Q3, and so on up to Qn. Let us consider a point P in the electric field of the charge configuration. Let the distances of Q1, Q2, Q3, and so on up to Qn from point P be R1, R2, R3, and so on up to Rn respectively. The potentials due to Q1, Q2, Q3, and so on up to Qn at point P in the electric field are represented by V1, V2, V3, and so on up to Vn respectively. Since electric potential is a scalar quantity, the net electric potential V at point P will be equal to the algebraic sum of the potentials due to the individual charges. Thus, it is V is equal to V1 plus V2 plus V3 and so on up to Vn. Substituting the expressions for the potential at point P due to individual charges, we get V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on up to Qn by Rn. Let this be equation 8. To obtain the potential due to a continuous charge distribution, we first divide it into a number of small volume elements of charge density ρ, such that the small volume elements have a volume dV each and a charge ρdV each. Then we find the potential due to each such volume element, say dV'. Then the potential V due to entire charge distribution is then obtained by integral dV', since this gives the sum of potentials over all such distributions. Now let us look at an example of uniform charge distribution. Let us consider a uniformly charged spherical shell of radius r, with a charge Q distributed over its surface. For any point P, which is at distance r greater than r, we have the potential due to the spherical shell at that point as V is equal to 1 by 4 pi epsilon naught Q by r. This equation holds good for all points that lie on the sphere or outside the sphere. Let this be equation 9. Since the electric field strength E for all points inside the spherical shell is 0, the electric potential has to be constant for all such points. The electric potential at any such point which is inside the surface will be equal to the potential on the surface and will be equal to 1 by 4 pi epsilon naught Q by r. We know that the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. That is, the work done to bring the charge Q0 from point S at infinity to P is equal to the potential energy of Q0 at point P. Since the force on charge Q0 due to any static charge configuration is F equal to Q0 E, the work done will be proportional to Q0. We can say that W is equal to a constant K into Q0, or the quantity W by Q0 is equal to K. Therefore, the resultant quantity obtained is independent of Q0. The work done per unit test charge is a characteristic of the electric field at that point due to the charge configuration and is known as electric potential at that point in the electric field due to the charge configuration. The electric potential is denoted by V. Let us consider a point P between the origin and point S. Then, potential energy of the charge Q0 at points S and P is US and UP respectively. We know that the work done by the external force to bring charge Q0 from point S to P is expressed as WSP is equal to delta U, which is equal to UP minus US. If Vp and Vs denote the electric potentials at points P and S respectively, then the work done by the external force to bring the unit positive charge from S to P is equal to Vp minus Vs, which is in turn is equal to UP minus US by Q0. Choosing S to be at infinity and also the electric potential at infinity as 0, the work done by the external force to bring the unit positive charge from infinity to point P in the electric field is equal to the electric potential Vp at point P. The electric potential V at any point in the electric field of a charge configuration is equal to the work done to bring a unit positive charge from infinity to that point in the electric field. Let us obtain an expression for the electric potential V at a point in the electric field of a point charge Q at the origin using the definition of the electric potential V at a point in the electric field of a static charge configuration. Consider the electric field of charge Q, in which P is a point at distance r from it. Consider the point S in the electric field, which is at distance r' from the charge Q. Let a unit positive charge Q0 with a charge of +1 coulomb be placed at point S. The electrostatic force Fe between Q and a unit positive charge placed at S will be equal to 1 by 4 pi epsilon naught into Q into 1 by r' square into r' cap, where r' cap is the unit vector along the direction of OS. Therefore, Fe will be equal to 1 by 4 pi epsilon naught into Q by r' square into r' cap. Let this be equation 1. Now let us move the unit positive charge from S towards P in the electric field by a small distance dr', and let dW be the work done in the process. The external force F required to move the unit positive charge is equal and opposite to the electrostatic force Fe. dW will be equal to F dot dr', which is equal to -1 by 4 pi epsilon naught Q by r' square into dr'. Let this be equation 2. We observe from equation 2 that the value of dW is negative, since charge Q0 is moved against the direction of the electric field. Now let us assume that the unit positive charge is brought from infinity to point P in the electric field. And let work W be done for this process. Then W is equal to integral dW. Let this be equation 3. Substituting the value of dW, we get W is equal to minus integral 1 by 4 pi epsilon naught Q by R dash square into dr dash in the limits ranging from infinity to R. Let this be equation 4. Since 1 by 4 pi epsilon naught Q are constants and evaluating only the integral, we have integral 1 by R dash square dr dash in the limits infinity to R is equal to minus 1 by R dash in the limits infinity to R, which is equal to 1 by R minus 1 by infinity. On further simplifying, we get W is equal to 1 by 4 pi epsilon naught Q by R. Let this be equation 5. This is the expression for the work done to bring a unit positive charge from infinity to R, which is equal to the electric potential V at point P. Therefore, the electric potential V at point P is equal to 1 by 4 pi epsilon naught Q by R, which is the expression for electric potential at P in the electric field of the point charge Q. Let this be equation 6. The electric potential V is a scalar quantity, and its SI unit is joule per coulomb or volt. 1 joule per coulomb is equal to 1 volt. We know that the electric field E of a point charge Q at a distance r from it is inversely proportional to the square of the distance r from it. The graph shows the variation of electric field E with respect to r. The electric potential V at a point in the electric field of a point charge is inversely proportional to the distance r from the charge as seen earlier. The graph shows the variation of the electric potential V with respect to distance r from the charge. The electric potential V at a point in the electric field can be positive or negative. This can be understood from the following solved examples. A point charge of 1 microcoulomb exists in air. Find the electric potential due to the charge at a distance of 10 centimeters from the point charge. Given that charge Q equal to 1 microcoulomb equal to 1 into 10 raised to the power minus 6 coulomb. Distance from the charge is r equal to 10 centimeter equal to 0.1 meter. The electric potential due to the point charge at distance r from it can be calculated using the formula V is equal to 1 by 4 pi epsilon naught into Q by R. The value of 1 by 4 pi epsilon naught is equal to 9 into 10 raised to the power 9. Substituting the values and calculating for V, we get electric potential V due to the charge at distance R equal to 9 into 10 raised to the power 4 volts. Solved example 2. Two charges, 2 microcoulomb and minus 4 microcoulomb, are separated by a distance of 20 centimeter in air. Find the electric potential at the midpoint of the line joining the two charges. Solution. Given charge Q1 is equal to 2 microcoulomb equal to 2 into 10 raised to the power minus 6 coulomb. Charge Q2 is equal to minus 4 microcoulomb equal to minus 4 into 10 raised to the power minus 6 coulomb. The distance of the midpoint from Q1 as well as Q2 is equal to R is equal to 10 centimeter is equal to 0.1 meter. At the midpoint of the line joining the charges, the potential is V is equal to 1 by 4 pi epsilon naught into Q1 by R plus Q2 by R. Substituting the values of the various given quantities and simplifying, we get V is equal to minus 18 into 10 power 4 volt. Consider an equatorial plane of the electric dipole as shown. For various points like A, B, and C, let the potentials be VA, VB, and VC respectively. Electric potential due to a dipole is given by V is equal to 1 by 4 pi epsilon naught into P cos theta by R square. Since points A, B, and C lie on equatorial plane, theta is 90 degrees for points A, B, and C. Therefore, VA, VB, and VC are equal to 0. Now let us consider a uniformly charged spherical shell of radius r with charge q on it. Imagine a sphere of radius r around the shell. The electric potential V for any point on the imaginary sphere is given by V equal to 1 by 4 pi epsilon naught q by r. In the above examples, we have seen surfaces which have the same potential at all points on them. Hence, potential difference delta V between points on an equipotential surface is 0. A surface on which the electric potential is the same for all points on it is called an equipotential surface. As potential difference delta V is equal to 0 between any two points on an equipotential surface, therefore, to move a test charge Q0 on the equipotential surface, the work done W is equal to Q0 into delta V is equal to 0. The equipotential surface at a point is always normal to the electric field at that point in the electric field for any charge distribution. Let us now look at some examples of equipotential surfaces. Assume a uniform electric field along the positive x-axis. Then, the planes parallel to the YZ plane represent equipotential surfaces. The concentric spheres around the charges in a dipole represent equipotential surfaces. The equipotential surfaces for a charge configuration consisting of two identical charges, minus q each, is shown. Consider two equipotential surfaces represented as A and B in a uniform electric field of strength E, separated by a small distance delta R. Let the potentials at A and B be VA and VB respectively. Let us consider a unit positive charge Q0 on the surface A. Suppose the unit positive charge is displaced from surface A to surface B in the direction of the electric field. The work done by the electric field W is equal to F delta R, where F is the force due to the electric field on the unit positive charge. As F is equal to Q naught E, and in this case, test charge Q naught is equal to +1 coulomb. We can say F is equal to E. Therefore, the work done W is equal to E delta R. Let this be equation 1. According to the definition of potential difference, the potential difference delta V is equal to VB minus VA, which is equal to the change in potential energy delta U of the unit positive charge while moving from A to B. Let this be equation 2. Now, delta U will be equal to minus W since there is a decrease in the electrostatic potential energy of the unit positive charge while moving from A to B. Substituting the value of W in the above equation, we get delta U equal to minus E delta R. Let this be equation 3. Equation 2 becomes delta V is equal to minus E delta R. Therefore, E is equal to minus delta V by delta R. Let this be equation 4. Equation 4 implies that in the direction of the electric field, the potential always decreases. Thus, VA is greater than VB. It also means that in a uniform electric field, the electric field strength is equal to the potential change per unit displacement, normal to the equipotential surface at that point. Now let us learn about the electrostatic potential energy of a system of charges. Consider a charge Q1 and let P be a point in the electric field of Q1 at a distance of R from the charge. The electric potential at P due to the charge Q1 is equal to V1, equal to 1 by 4 pi epsilon naught into Q1 by R. Let this be equation 5. Now, to bring a charge plus Q2 from infinity to point P in the electric field against the electrostatic force, the work done W is equal to Q2V1. Let this be equation 6. Substituting equation 5 in equation 6, we have W equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. This work done against the electrostatic force is stored as electrostatic potential energy U in the system of charges. Electrostatic potential energy U stored in the system of charges is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. Let this be equation 7. From equation 7, we see that the electrostatic potential energy is independent of the spatial location of the charges in a given medium and is mainly dependent on the separation R between the charges. The electrostatic potential energy is a scalar quantity and can be positive or negative depending on whether the product Q1, Q2 is positive or negative respectively in the equation 7. When both the charges are either positive or negative, the electrostatic potential energy is positive. That is, the work done to bring a charge Q2 from infinity to point P is positive. Also, when the charges Q1 and Q2 are unlike, then the work done to bring Q2 from infinity to point P is negative. Equation 7 gives the electrostatic potential energy for a pair of charges Q1 and Q2. Proceeding similar to the above procedure, for a system of 3 charges Q1, Q2 and Q3, there would be 3 pairs in the expression for the electrostatic potential energy U, given as U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2. R23 is the separation between Q2 and Q3. And R13 is the separation between Q3 and Q1 respectively. Let this be equation 8. Equation 8 can be expressed as U equals to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus 1 by 4 pi epsilon naught into Q2 Q3 by R23 plus 1 by 4 pi epsilon naught into Q1 Q3 by R13. This equation can again be written as U is equal to U12 plus U23 plus U13. Let this be equation 9, where U12, U23 and U13 are the electrostatic potential energies for the pairs of charges Q1, Q2, Q2, Q3 and Q1, Q3 respectively. The above procedure can be adopted for calculating the electrostatic potential energy of a system of n charges as well. From the above discussion, we see that the potential energy of a system of charges is a characteristic of its present state only. We know that electrostatic potential energy U for a system of 3 charges Q1, Q2 and Q3 can be calculated using the formula U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2. R23 is the separation between Q2 and Q3. And R13 is the separation between Q1 and Q3 respectively. Let this be equation 1. Equation 1 can also be written as U is equal to U12 plus U23 plus U13. Let this be equation 2. In equation 2, U12, U23 and U13 are the electrostatic potential energies for the pairs of charges Q1, Q2, Q2, Q3 and Q1, Q3 respectively. Let us now derive an expression for the electrostatic potential energy of the system of charges in terms of the potentials. Let V be the potential at a point P1 in the electric field E produced by a source charge. Here, R1 is the position vector of the point with respect to the origin. Let us consider a charge Q1 at infinity from point P1. If W1 is the work done to bring the charge Q1 from infinity to the point P1 in the external field, then the external electric potential at the point P1 is V of R1 equal to W1 by Q1. This implies that W1 equal to Q1 into V of R1. Here, we assume that the potential due to the source charge at infinity is 0. This implies that V of R1 is also the potential difference between the point and infinity, which is delta V. Now, if Q1 is released at point P1, it moves away in the direction of the electric field to infinity and gains kinetic energy equal to W1 when it reaches infinity. If V of R1 is plus 1 volt, then the potential difference between the point P1 and infinity is delta V equal to V of R1 minus V infinity, which is equal to plus 1 volt. Now, if Q0 is an electron which is at rest at infinity, is released under a potential difference, then it moves towards the point P1. Since P1 is at higher potential compared to the point at infinity, the electron gains kinetic energy, which is equal to Q0 into V of R1. The magnitude of the charge on the electron is 1.6 into 10 power minus 19 coulomb, and V of R1 is equal to 1 volt. Therefore, the kinetic energy gained will be equal to 1.6 into 10 power minus 19 joule. This kinetic energy gained by the electron is called 1 electron volt. Electron volt is defined as the kinetic energy gained by an electron when accelerated under a potential difference of 1 volt. We have seen that the work done to bring a charge Q1 from infinity to point P1 is given by W1 is equal to Q1 into V of R1. Now let us consider another point P2 in the electric field, whose position vector with respect to the origin is R2, and the external potential at the point is V of R2. Let the distance between points P1 and P2 be R12. Let us bring another charge, Q2, from infinity to the point P2 in the electric field, and let the work done in this process be W2. Hence, work done to move the charge Q2 from infinity to the point P2 is Q2 into V of R2. If Q2 is now released, it moves due to electric field E and also due to the electric field of Q1. Work has to be done to hold the charge Q2 against the force due to the electric field E and also due to that of Q1. Work done to hold Q2 against the electric field due to Q1 is expressed as W12, which is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12. The total work done to hold Q2 at rest at P2 is Q2 into V of R2 plus W12. Substituting the relation for W12, we have total work done is equal to Q2 into V of R2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. The total work done to assemble the system of charges in the external electric field is equal to Q1 into V of R1 plus Q2 into V of R2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R12. This is stored as electrostatic potential energy in the system of charges. Let this be equation 3. Now, let us derive an expression for the electrostatic potential energy of an electric dipole in a uniform external electric field of strength E. Consider an electric dipole placed in a uniform electric field of strength E directed along the positive x-axis. The axis of the dipole makes an angle theta with the direction of the electric field. The dipole has charges plus q and minus q separated by distance 2a. Hence, its electric dipole moment P is equal to 2aq. The dipole, when placed in a uniform electric field, experiences a torque tau, which is equal to P cross E equal to P sin theta. Let this be equation 4. This torque rotates the dipole until it is aligned in the direction of the external electric field. Let us apply an external torque tau external equal and opposite to the torque tau, which rotates the dipole from the angle θ1 to the angle θ2, with the field direction without giving the dipole any angular acceleration. That is, at an infinitesimally low angular speed. Let the work done by the external torque in this process be W. Then, W is equal to integral tau external dot d theta in the limits θ1 to θ2, as tau external is equal to tau. We can write W is equal to tau into d theta in the limits θ1 to θ2. Substituting tau equal to P into E sin theta, we get W is equal to integral P E sin theta d theta in the limits θ1 to θ2. Since P and E are constant, we keep them out of the integration, and thereby, carrying out the integration, we get W is equal to minus PE into cos theta 2 minus cos theta 1. This work done by the external torque gets stored as potential energy U in the system in the external electric field. If θ1 is equal to 90 degrees and if θ2 equal to theta, then the potential energy in terms of the angle the dipole makes with the external field is U is equal to minus P into E cos theta. We can express P E cos theta as P dot E. Then, potential energy U of the dipole is expressed as U equal to minus P dot E. If V of R1 and V of R2 denote the potentials at the positions of the charges plus Q and minus Q of the electric dipole respectively, the axis of the dipole makes an angle theta with the direction of the electric field, and the distance between the charges R12 equal to 2a. Then, substituting Q1 equal to plus Q and Q2 equals to minus Q in equation 3. And simplifying, we get potential energy U of the system as U is equal to plus Q into V of R1 plus minus Q into V of R2 plus 1 by 4 pi epsilon naught into minus Q square by 2a. This equation can be further simplified as U is equal to Q into V of R1 minus V of R2 minus 1 by 4 pi epsilon naught into Q square by 2a. We can further simplify VR1 minus VR2 as follows. V of R1 will be less than V of R2, since potential decreases in the direction of the field. We can say dV is equal to V of R1 minus V of R2, which is equal to minus EdR. Since dV is equal to minus EdR, from the figure, dr is equal to 2a cos theta. Therefore, V of R1 minus V of R2 will be equal to minus 2a cos theta into E. Multiplying both sides with Q, we get Q into V of R1 minus V of R2 equal to minus Q into 2a cos theta into E. Hence, Q into V of R1 minus V of R2 can be written as minus 2aq cos theta into E. And since dipole moment P equal to 2aq, this can be written as minus Pe cos theta. Now the electrostatic potential energy of the system can be written as minus Pe cos theta minus 1 by 4 pi epsilon naught q square by 2a. If the electric dipole were perpendicular to the field direction, then the potential V of R1 will be equal to V of R2, and hence Pe cos theta will be equal to 0. And hence the electrostatic potential energy of the system will be equal to minus 1 by 4 pi epsilon naught q square by 2a.